So, my thesis is about the computation and the avoidance of the singularities of robot manipulators. There are many kinds of robot manipulators. For example, we have serial ones, or we have parallel ones like this one, or like this one used for pick and place operations. There are also spherical ones like this one used to orient a camera, and of course there are spatial ones like this driving simulator. And we even have manipulators that are driven by cables. One thing that is common to all these robots is that they move to achieve their task. So they have motion capabilities. And the fundamental problem in robotics is the study of these motion capabilities. And in this general context, there is one important problem that is to study the singular configurations, where important changes on these motion capabilities may happen. And we can see that with an example. In this manipulator, in a regular configuration, the platform is fixed when the actuators are locked. But if we move it to a singular configuration, you can see that the platform can move even if the actuators are locked. And in addition to that, human intervention is needed to bring back the manipulator to normal functioning. This kind of phenomenon can also be found in spatial manipulators like this exact light. In a regular configuration, the platform is stiff when the actuators are locked, but the platform loses rigidity in a singular configuration. So two important problems arise related to the singularities. Because for the design and the operation of a robot, it is important to have means to be able to compute the singularities, but also to be able to avoid them. So what has been done so far on this topic? Investigation of singularities started to gain momentum in the early 80s, but initially most works were restricted to specific manipulators, especially serial ones. And by the end of the decade, there was no method allowing to study the singularities of a manipulator with an arbitrary architecture. The first attempt to provide a general framework for the characterization of the singularities can be attributed to Gosselin and Angeles. And their approach was sound, and it allowed to deal with more complex manipulators containing closed kinematic chains. However, it was later found that further singularity types existed that could not be framed in their formalism, and this observation led Zlatanov to define the singularities in a more general way. After these works, there were many approaches to compute the singularity sets that appeared. Some examples of them are the works by Santonja and collaborators, Bonev, Lee and collaborators, or Merlet, who provided methods to compute the singularity sets for specific manipulators. And these are just some of the many references available on this topic. With respect to the problem of avoiding singularities, there are not many works, but some of them are those by Dasgupta and Mrutyunjaya, Sen and collaborators, or Zhang and Gosselin, who provided methods for the Stuart platform. So the advances in the field are significant, but most of these methods restrict their attention to particular types of manipulators. And some of them work very well and are very efficient, but the lack of a general procedure does not allow the analysis of new or alternative manipulators. So this thesis aims to cover this gap by providing reliable methods for these two problems for manipulators of a general architecture. So in the problem of computation, given a manipulator with designated input and output coordinates, we want to find from its configuration space all points that correspond to singular configurations. In contrast, in the problem of avoidance, we start with two different configurations of a manipulator, which are represented by 2 points on the configuration space, and we want to find a path between them that avoids the singularities. So what are our assumptions for these problems? We would like to solve these problems for general architecture manipulators with lower perijoins, whether they are planar, spherical, or spatial, and with any multibody system topology. Also, we have restricted our attention to the non-redundant case for the sake of simplicity, but the development should be extendable to the redundant case as well. And finally, we have not considered the possible collision between the bodies because this adds considerable complexity to the problems and usually can be dealt with a posteriori. So now I will divide the rest of the talk in 3 parts. First, I will provide a definition and a geometric interpretation of the singularities. Then, I will explain the methods that we propose for the problem of singularity set computation. And then we will see the methods that we propose for singularity avoidance. So we can start now with the definition of singularities. All the possible configurations of a manipulator can be characterized by a system of equations that expresses the assembly constraints between the various bodies of a manipulator. And the set of all these feasible configurations is known as the configuration space of the manipulator. In addition, for a given configuration, it is possible to find a velocity equation like this one that gives all possible motions of the manipulator at that configuration. And this equation can be found in several ways, for example, by differentiating the assembly constraints or using tools of screw theory or by other means. And here the matrix L depends on the configuration Q, and M is a velocity vector which globally characterizes the velocity state of the manipulator. And we can distinguish three subvectors in M. First, we have the vector mu of output velocities relative to the functionality of the manipulator. Then we have the vector mv of input velocities, which represent the velocities of the actuated joints. And then we have the vector mp, which encompasses the rest of velocity coordinates, in particular those of the passive joints. So in this context, the instantaneous kinematics analysis of a manipulator usually addresses two main problems. The forward instantaneous kinematics problem, where given the input velocities, we want to find the whole velocity state of the manipulator. And the inverse instantaneous kinematics problem, where given the output velocities, we want to find the velocity state of the manipulator as well. So a singularity is defined as those configurations where either of these problems becomes indeterminate. For example, if the forward problem is indeterminate, the input velocities mv do not determine a unique value for m, and these are called forward singularities. If the inverse problem is indeterminate, the output velocities mu do not determine a unique value for m, and these are called inverse singularities. In addition, it can be seen that the forward and the inverse singularities are those configurations where two matrices are rank deficient, Ly and Lz. And these are just the submatrices of L obtained by removing the columns corresponding to the input velocities and to the output velocities. So, to understand these singularities from a kinematic point of view, we will now see the geometric causes of the rank deficiency of these two matrices. For that, as a simple example, imagine that our configuration space is just a sphere, and that we obtain the velocity equation by differentiation of the assembly constraints. This equation already reveals that for a given configuration, the possible velocities, q dot or m, are vectors in the tangent space of this configuration. So a first possible cause for the rank deficiency of Ly or Lz is when the whole matrix of the velocity equation, L or Q, is rank deficient. When this happens, this tangent space does not exist. And this corresponds to non-smoothnesses of the configuration space, like bifurcations, sharpnesses, or dimension changes. And these are called C-space singularities. And since they are intrinsic to the configuration space, they do not depend on the choice of input or output coordinates. So, leaving out these configuration space singularities, we can see what happens in a regular configuration by considering the spaces of input and output coordinates. Note that if we choose an input velocity vector, this corresponds to a unique vector in the tangent space. And if we choose an output velocity vector, this also corresponds to a unique vector m in the tangent space. But those configurations where Ly is rank deficient correspond to special positions of this tangent space, such that it projects to the inputs as a space of lower dimension. And see that here, if we choose an input velocity vector, this does not correspond to a unique vector in the tangent space. And this corresponds to control issues of the manipulator. A similar thing happens on the other side when Lz is rank deficient. Here, no matter what vector we choose on the tangent space, all of them project onto a line in the output space. And this corresponds to losses of dexterity of the end effector. The first kind are called input singularities, and the second kind are called output singularities. And note that there may be points, like this one, that are both input and output singularities. An example of input singularities can be seen with the previous example of the exact line manipulator. These are the most important singularities in parallel manipulators, and you can see here that the platform loses rigidity even if the actuators are locked. An example of output singularities can be seen with this serial manipulator, where you can see that the manipulator moves even if the end effector is fixed. And these are usually the most important singularities appearing in serial manipulators, but they can also happen in manipulators with closed kinematic chains. Finally, note that the singularities can be seen as silhouettes of the configuration space relative to the projections to the input and to the output spaces. And this provides a powerful geometric image to understand the singularities. In this thesis, we provide methods to compute these singularities. And we will see that the projections to the input and output spaces provide much information on the motion capabilities of a manipulator. So to summarize, we have two main types of singularities: the set of forward singularities and the set of inverse singularities. And these two sets can intersect, in fact. The configuration space singularities lie at the intersection of these two sets. And then the input singularities are those forward singularities which are not C-space singularities. And the output singularities are those inverse singularities which are not C-space singularities. The definition of the singularities allows us to write systems of equations that characterize them. For example, in the forward singularities, the matrix Ly is rank efficient. So there must be a non-null vector in its kernel. So we can write this system of equations whose solutions are the forward singularities. Similarly, we can write this system of equations for the inverse singularities using the matrix Lz. In these two systems, the first line just constrains the vector q to be a valid configuration of the manipulator. And the second and third lines just impose the rank efficiency of the matrices Ly or Lz. So following this, the whole singularity set of a manipulator can be found as the union of the solution sets of these two systems of equations. So now we will see how we propose to compute this singularity set by solving these two systems of equations. Usually, the solution of nonlinear systems of equations like these ones involves a first step of formulating the equations algebraically, and then a resolution step where some numerical technique of polynomial system solving is used. So a good solution to each of these problems treated as independent problems does not necessarily lead to a good solution of the overall problem. So our aim has been on finding a good combination of formulation and resolution so that the whole process becomes simple to understand and implement, but also efficient in practice. So in our case, the formulation step just entails writing the systems of equations from the assembly constraints and the velocity equation of the manipulator. And in the resolution step, we need to take into account several issues. For example, the singularity set is usually of codimension 1 with the configuration space. So we may have to deal with 0, 1, or 2-dimensional sets, or even higher. Also, the singularity set itself may present some accidents even if the configuration space is smooth, like, for example, dimension changes, bifurcations, or several connected components. So the method that we choose should be able to deal with these two difficulties. Most of the methods of polynomial system solving can be classified into two main groups. First, we have the algebraic geometric techniques. These methods apply elimination to reduce the initial set of equations to a minimal set of polynomials. And the roots of these polynomials, once back substituted, yield the original solutions that were sought. However, these methods are usually designed for 0-dimensional solutions, so they are not suitable for our needs. Another group of methods apply continuation techniques. The most typical ones start with a system of equations whose solutions are already known, and they transform the system into the original system of equations while tracking the solutions along the way. So at the end, they obtain the solutions that were desired. These systems are usually designed for 0 or at maximum 1-dimensional sets, but some new recent developments by Wamper and his collaborators has led to new methods able to deal with higher dimensional sets. However, these methods do not provide an explicit representation of the solution set, and they work in the complex domain, which adds extra cost when only the real solutions are required. Another extension of continuation methods has been proposed by Mike Henderson from IBM, and which is known as higher dimensional continuation methods. We initially thought that these methods could be used to compute the singularity sets, but after a collaboration with the author, we concluded that the methods are yet not robust enough to deal with all the accidents that the singularity set may present. So given this situation, we propose to use a branch and prune technique. These methods work applying exclusion. They start with an initial box bounding the whole solution set, and then they iteratively remove empty portions of this box until finding of approximation of the solution is obtained. So to see how this works, we can see an example. Imagine that we have a system of equations with just two equations, the equation of a sphere and the equation of a cylinder. So the solution of this system of equations is their intersection, which is this blue curve here. So the method starts with a box that contains the solution, and iteratively we apply branching and pruning until a good approximation of the solution is found. So here the branching operation is trivial because it only entails bisecting a box. But the pruning operation is more complicated. We show in the thesis how, using reference point coordinates, it is possible to write these systems of equations so they adopt a quadratic form, meaning that they only have linear, quadratic, or bilinear terms. And this leads to a quite simple and easy to implement pruning operation. To understand how this pruning operation works, imagine that we only have a linear equation and a quadratic equation. And we also have this initial box that contains the solution, which is the intersection between the two equations. So if we only consider the linear equation, we can reduce the initial box to this smaller box here. But if we also consider the quadratic equation, we can approximate it by its linear relaxation inside the box, which is formed by two half planes. So taking into account all these linear restrictions, we can reduce the original box to this small box here that still contains the solution of the system. The systems of equations that we solve with this method are quite big, and this pruning operation is costly, is computationally costly. But an advantage is that the method can be parallelized in a very natural way. At each moment we have several boxes that await for this reduction process. So we can have a main processor that distributes these boxes among several other processors, and each one of them performs this reduction operation in parallel. So at the end we have a method that is complete in the sense that all solutions will be enclosed by some box when the computation finishes. So we are sure to obtain all the solutions of the original systems of equations. So with this method, if we have a manipulator with a configuration space like this, we are able to compute the forward and the inverse singularity sets. But something that it is not trivial is how to represent them, because they are usually defined in a higher dimensional space. So the use of projections to the input or output spaces is necessary. However, these projections already provide us many information about the motion capabilities of the manipulator. For example, if this is the projection to the output space, the projected singularities inform us about the limits of the workspace. Also, since we can project both the input and the output singularities, we can see in which points we may find control issues or dexterity losses. And in addition, these projections could reveal if there are several connected components. An advantage of the method also is that the singularities are computed directly in the configuration space. So the projection to any set of variables is directly available. And we can see now that in some examples. We consider here a 3RRR manipulator, which consists of a platform that is driven by 3 legs. And each leg has 3 revolute joints. Here the output of interest is the motion of the platform. And we consider that the actuators are in the intermediate joints of each one of the legs. If we write here the systems of equations for the forward and inverse singularities, we obtain systems with 29 equations and 31 variables. So we solved these systems and we projected the obtained sets to the input spaces initially. And the input space is the space of these 3 intermediate angles. And we obtained these surfaces. Here the red surface corresponds to forward singularities, which are those configurations where these 3 lines intersect. The blue surface are the inverse singularities, and it corresponds to configuration where one of the legs is fully extended or folded back. With our method, we can also compute the slices of these surfaces just by fixing the value of some variables. For example, if we slice in this direction, we obtain these slices. You can see that here, as expected, the singularities are just curves. We have the forward singularities in red and the inverse singularities in blue. But there are two slices that are more interesting, which correspond to the intermediate angle of one leg being 0 or pi, here or here. In this case, you can see that the inverse singularities in blue are no longer curves, but surfaces. So there has been a sudden change on the dimension of the inverse singularity set on these slices. And our method has no problem in computing them as well. And this, in fact, is in agreement with the fact that the platform is in an inverse singularity whenever a leg is fully extended or folded back. Since we computed these singularity surfaces directly on the configuration space, we can project them as well to the post variables of the platform. And we obtain this projection. In this example, the blue surface are the inverse singularities and contain around 200,000 boxes and were computed in around 300 seconds. And the red ones, which are the forward singularities, contain a similar amount of boxes and were a little bit more costly to compute. These surfaces seem to be very complicated, but it was shown by Bonnet and Gosselin that the constant orientation slices of these surfaces contain only conic curves for the forward singularities. So if we compute these slices, we can see that only pairs of lines, parabolas, or ellipses appear. But it is not always this simple, because if we just change the actuators from the intermediate joints to the joints on the base, those slices now look like this. Here, the forward singularities in red are implicitly defined by polynomials of degree 42. So you can see that this is quite more complex than the previous slices that contained only conic curves. But our method can compute them as easily as before. To see how the method works in spatial manipulators, we can compute some singularities of the Stuart platform. In this manipulator, the most important singularities are the forward singularities, because in the majority of designs, the limits on the joints do not allow the appearance of inverse singularities. But if we had a design that allowed the appearance of inverse singularities, we would be able to compute them as well. The configuration space of this manipulator is 6-dimensional, so the singularity set is in general 5-dimensional. So even if we were able to compute it, we would not be able to see it. So this is usually solved by computing some slices of interest. For example, one slice of interest is when the platform moves at a constant orientation, and we obtain this surface for the forward singularities. Another slice of interest is when the platform moves with one point fixed, so it can only rotate, and we obtain this slice at a constant position. All the points in these surfaces correspond to configurations where the placar coordinates of the lines are linearly dependent. And if we look at some computation data, we can see in the last line that the constant position slice was much harder to compute than the constant orientation slice. And this is because the system contains more equations and more variables, but also because the equations contain many more nonlinearities than in the other case. In addition to compute forward and inverse singularity sets, we can also compute other types of singularities. It can be found in the literature some definitions of other lower level singularity subsets. For example, Zlatanov defined 6 different types, which are redundant input and output singularities, impossible input and output singularities, redundant passive motion, and increased instantaneous mobility singularities. Each one of these types describes a different change in the kinematic properties of a manipulator. And we were able to write systems of equations that characterize each one of these types independently. So we can use the same method to obtain these types independently. We show that in the thesis with a simple but challenging example of a manipulator with 2 degrees of freedom. Here, for example, we have in blue the configuration space of this manipulator, and each one of the cubes with different colors corresponds to each one of these types computed independently. All this machinery of singularity set computation can also be used for workspace boundary determination. In this case, however, since the joint limits usually greatly modify the shape of a workspace, we can take them into account in the assembly constraints that define the configuration space. So clearly, the workspace of a manipulator is the projection of the configuration space to the output variables. It is also clear that in the boundary of this workspace, some loss of mobility has to happen with respect to the output variables. So a necessary condition for a configuration to be on the boundary is to be an inverse singularity. However, this is not a sufficient condition because we may have inverse singularities that project on the interior of the workspace, like in these two additional examples. The first two examples here represent actual barriers of motion with respect to the output singularities, because any path on the configuration space through them remain on the same side of the projected singularities, because they locally cannot be crossed. And this is why we call them boundary barriers and interior barriers. And if we want, we can mark them in the projection with normal vectors on the forbidden side. In the last case, however, we can have paths in the configuration space that cross the projected singularity. And this is why we call them traversable singularities. An example of each one of these types can be seen with a simple 3-arm manipulator where the first revolute joint is constrained to move in this range of motion. This is the workspace relative to the position coordinates of the tip point of the last link. And these are the computed singularities where some loss of motion can happen. Here we have an example of a boundary barrier. This configuration is in an interior barrier, and this is an example of a traversable singularity. And in the thesis, we explain a way to classify the computed singularities among these three types. So if we want, we can enrich this diagram by identifying the actual barriers of motion. So this, together with the method of singularity set computation, provides us with a powerful method of workspace determination that can be applied to manipulators with a general architecture. And in addition to that, we are not constrained to compute the workspace with respect to the output variables only. We can compute it with respect to the input variables as well, for example, or to a subset of the output variables, like in this example. There are many methods of workspace computation, but they are for specific manipulators, and here we just highlight some of them. Our method can only be compared in terms of generality, as far as we know, with a method due to Hauck and his collaborators, which uses a similar approach. He also computes these singularities and then classifies them, but the method that he uses to compute these singularities is completely different, and in fact it has some problems because it may lose some of these singularities. It has problems especially when there are multi-component workspaces or when there are voids or degenerate barriers. And we will see now with some examples that our method has no problems in these three situations. This is the double butterfly linkage, where we have added two slider joints on each side to allow it to move with 3 degrees of freedom. So with respect to the position coordinates of this point, we obtain these singularity curves which delimit 3 different regions of the workspace. The method by Hauck is only able to obtain the component relative to a given initial configuration, while we are able to compute all 3 of them. And if now we apply the classification process to the lower component, for example, we can obtain a representation like this one. To see the problem of voids, we can compute some workspace of the Stuart platform. For example, here we have the constant orientation workspace, which looks like an umbrella more or less, and here we have some of its slices. The method by Hauck resorts to ray shooting techniques to hit the boundary, and we can see, for example, in this slice, that some of the voids become occluded by others if this is the original configuration. So he would not be able to compute these two voids, while our method has no problem in computing them. And finally, to see the problem of the degenerate barriers, we can consider the class of spherical manipulators like this one. If we compute the singularities here, we obtain a surface, this surface. And here in the bottom, you can see the projections of this surface with respect to the coordinate planes. If we choose some specific design parameters for these manipulators, this surface degenerates into one-dimensional curves, which is the case of the well-known agile line manipulator, where we have these singularities. In this case, the method by how would not be able to hit any of these curves because they are of lower dimension than expected, but our method can compute them as well. So, with this, we have presented the methods that we propose for singularity set computation. And now we can go to see the methods that we propose for singularity avoidance. With all these previous techniques, we can introduce projections of the singularity sets to the input and output spaces, which provide rich information on the global shape of the configuration space and the singularities. These projections can also be used as safe navigation maps, if you want, because a path in the projection that does not cross a singularity necessarily corresponds to a singularity-free path in the configuration space. But not all singularity-free motions are represented in the projections, as in this example. We have here a singularity-free motion in the configuration space, which seems to cross the singularities in the projection. So, in order to take full advantage of the motion capabilities of a manipulator, we need a singularity-free path planner to tell us if two configurations can be connected through a singularity-free motion. Or in other words, we need a way to navigate the singularity-free configuration space of the manipulator. So, to see how we propose to do that, I will first explain that we can formulate the singularity-free configuration space as a system of equations. And then we will see that we can use a higher dimensional continuation technique to explore the solution of this system of equation in order to find these singularity-free paths. To do that, we can imagine a very simple example. Here, imagine that our configuration space is just a plane. So this plane is the solution of our assembly constraints. And in this configuration space, we can have some singular curves. In these curves, there is a matrix that has zero determinant, because as we have seen before, it is rank deficient. So we can write these two conditions that characterize the singularity-free part of the configuration space. And here we want to solve the problem of connecting the start and goal configurations. So in order to apply a continuation method, we need to transform this condition to an equation. And to do that, our approach is to add a new dimension to the problem B and to change this condition by this equation. So basically, what we are doing is that we are modifying the shape of the configuration space by elevating each point to the inverse of the determinant. And in this way, we are sending singularities to infinity. There is a one-to-one correspondence between the points of the singularity-free configuration space and the points on this new extended manifold. So this allows us to find the corresponding points to our start and goal configurations. And this also allows us to transform the problem of computing a path in the configuration space to the problem of computing a path in this new extended manifold. And this new extended manifold, in fact, retains the connectivity of the singularity-free configuration space. We can also see that the Jacobian of this system of equations is never rank deficient. So this extended manifold is in fact a smooth manifold. And this is very convenient to apply a continuation technique because we don't have to worry about the presence of non-smoothnesses like bifurcations, for example. And note that if we want to define a clearance with respect to the singularities, the only thing that we need to do is to set a maximum allowed value for the variable b. So now that we have these systems of equations that characterizes the singularity-free configuration space, we will see the higher dimensional continuation technique that allows us to explore the solution of this system of equations. A higher dimensional continuation method is able to obtain the atlas of a manifold by iteratively expanding the charts from an initial configuration. So at the end, we obtain a collection of charts that provide altogether a parametrization of the underlying manifold. So let's see how this expansion works. Imagine that this is the manifold that we want to explore, and we have an initial configuration. So the first step is to initialize the first chart, and this is done by defining a ball on the tangent space of this configuration, together with a polytope that tightly encloses this ball. Then we have to select a point on the ball. This can be done, for example, by selecting a corner and finding the intersection with the ball. And then we project this point to the manifold. This new point provides us with a potential new center of a new chart. But we have to test its validity before. For example, by checking that this distance to the tangent space is not too big, or that the new tangent space on this new point is not too different from the previous tangent space. But if the point is okay, we can initialize a new chart as before, and then we crop the two charts in a coordinate manner so as to ensure a smooth coverage of the underlying manifold. Now the expansion could continue by choosing any other of the corners of these polygons. Note also that the neighbor charts crop the original polytope until all the polytope is inside the original ball. When this happens, we say that the chart is closed and does not need to be expanded anymore. So this is a systematic algorithm for continuation, but in our case we don't need to compute the full atlas to find singularity-free paths. So we have extended this method to also deal with problems of path planning by defining a strategy to select the next chart to expand. So we can guide the exploration from the start to the goal. We have several options here. For example, we can define a distance function, and then the next chart to expand will be the one that's closer to the goal. For example, here the next chart to expand would be this one, and then this one, until we finally reach the goal. So the algorithm finishes when the goal is found, or when the whole atlas of the manifold has been computed, in which case there is no path between the start and the goal. And of course we can combine this distance function with any other strategy of expansion that we want, for example an A* strategy. So this is a resolution complete method in the sense that it will find a path if it exists, or it will prove non-existence of the path otherwise. So now we will see some examples of how this works. And in these examples, we have used an A* strategy combined with an Euclidean distance on all the variables of the problem. So we can consider this 3RRR manipulator with the actuators on the base joints. Before we have obtained this projection of the singularity sets when the platform moves at a constant orientation. So if here we want to connect these 2 points, it may seem impossible to do without crossing singularities. But in this case, we can take advantage of the fact that the platform can move at different working modes corresponding to the flippings of the legs. So for example, if we start with this configuration, only these singularities appear, and we can see that the start and the goal are directly connectable. So with our method, we obtained this path, which was computed quite fast in a desktop computer like this one. And here we have the path in green, and the shaded blue area is the part of the atlas that was actually explored to obtain this path. Another thing that we can do with this method is that we can compute the whole component of the singularity-free configuration space that is available from the start configuration. For example, in this case, we obtain this atlas. And an advantage to have an atlas like this is that any subsequent planning query here can be solved in milliseconds from the graph defined by all the charts and all the relations of neighborhood. But the problem is a little bit more interesting when we allow the platform to change its orientation. So now we will have a problem of path planning in 3 dimensions instead of 2. We will ask the platform to perform this motion in 3 steps. And we will start from this configuration. Now I will play the video of the path that we obtained, and you will see that the singularities and the workspace change while the platform is moving. And this is because at each moment we are showing the constant orientation slice of the singularity sets that correspond to the orientation of the platform. So this is the path that we obtained. You will see that this point never crosses a singularity, and that the algorithm by itself is able to take advantage of the change of working mode. For example, now this leg will change working mode, and this leg will also change working mode now. And these paths were computed in just 1 second. Here I have shown the singularities and the workspace while the platform moves, but this was just for clarity. The algorithm itself does not need to compute any of these things to obtain the path. And this is in contrast to other methods which are computationally very intensive because they represent the singularities explicitly as obstacles. So with this method, so far we have defined the clearance with respect to the singularities in terms of the determinant of a Jacobian matrix. Some people argue that this does not have a clear physical meaning, but in the early stages of design, only the kinematic architecture of the manipulator is known, and other information leading to more physically meaningful clearances is just not available. So our planner already covers the needs of a robot designer in the early stages of design. But for other design stages, or even for motion planning during operation, we could consider other information. For example, the actuator's accuracy, or the maximum and minimum allowed forces, or the maximum possible velocities, or even the link inertias. And we will show here that it is possible to add these further constraints in the planner in the case that we know the maximum and minimum allowed forces, and I will exemplify that in the case of classical or cable-driven hexapods. And the clearance that we will obtain is the one that results from allowing only range-feasible configurations. It is known that given a range in the platform, this translates into some forces in the legs. And one problem near the singularities is that some of these forces can get very high, leading to breakage of the manipulator. So one way to stay away from these problems is to ask to the platform to move while maintaining the forces always within their allowed limits. This is in fact inspired by the notion of range-feasible workspace in the works by Boscher and Uber. But here, to model the fact that this range can be subject to perturbations or to uncertainty, we will also ask the platform to be able to balance all ranges inside a 6-dimensional space of ranges, while the forces are still between their allowed limits. So we have modeled this region as a 6-dimensional ellipsoid in the space of ranges, which can be mapped to the space of the legs forces as an ellipsoid as well. So the only thing that we need to do is to check that this ellipsoid remains inside the box defined by the limits of the forces on the legs. And note here that if we are dealing with a cable-driven manipulator, the only thing to take into account is that these minimum forces allowed on each leg have to be positive in order to maintain tension in all the legs at all time. So in the thesis we have shown how all these restrictions can be written as a system of equations that characterizes the range-feasible C-space. And we have also shown how this range-feasible C-space only contains non-singular configurations, and that also it is a smooth manifold. And this allows us to use the same continuation technique as before to explore the solution of this system of equations and find range-feasible paths. We can show that with some examples. Here we have this cable-driven manipulator, which is inspired in the NIST RoboCrane. And I can show you two paths computed when one point of the platform is fixed and the torsion of the platform is also fixed. Here in green, the green mesh is the whole atlas, and the shaded areas correspond to the parts of the atlas that were actually explored to compute each one of the paths. The first path was computed in just 20 seconds, but the second path is more interesting because it contains narrow corridors, which usually pose problems to other path planning methods. But in our case, as long as the narrow corridors are below the clearance limit, the method has no problem in crossing them. And in fact, we can check that the forces always remain inside their limits along their path, along the whole path. To show an example of path planning, in this case in 3 dimensions, we can allow the platform to also move in their vertical axis. So in this case, the charts will no longer be polygons, but will be polyhedra. And we can see here in green this polyhedra, which is the atlas that was explored to obtain this range-feasible path that can be seen inside. We are currently implementing this method in a prototype of this manipulator, which can be seen here. And with our method, we will be able to avoid those configurations where the tension of some cable is lost, like here, which you can see that these situations are not difficult to find. You can see. So now we can finish with some conclusions of the thesis. This thesis contributes with methods of singularity computation and singularity avoidance. With respect to the computation of singularities, we have provided a method able to compute the whole singularity set of a manipulator and to identify the various singularity types in it. And we have extended this technique to also compute the various workspaces of a manipulator and the motion barriers that may be present in its interior. With respect to the singularity avoidance, we have provided a method to compute singularity-free paths between given configurations. And we have seen how other constraints can be taken into account when more information on the manipulator is available. All these results have been published in 7 conference publications and have been the subject of 6 journal papers. These 3 works here are joint work with Professor Zlatanov, and these 2 are joint work with Mike Henderson. And an implementation of all these methods and some others is available through the Quick Suite Toolbox, which will be presented in the Computational Kinematics next week, and also in the Robotics and Automation magazine. And to finish, I would like just to provide some possible directions of future work. With respect to the computation of singularities, a natural continuation of this research would be to adapt the methods so they can deal also with redundant manipulators. Also, we have seen how the analysis of the various singularity sets requires a profound and detailed study. So it would be desirable to further illustrate the performance of the method by applying these methods to more challenging manipulators. And also, robot designers usually tend to produce symmetrical designs, and this usually translates to symmetries of the configuration space and of the singularity sets. So it would be interesting to be able to exploit these symmetries in order to focus the computational effort. With respect to the avoidance of singularities, the planner that we have presented shows a computational cost that scales exponentially with the dimension of the explored manifold. So in order to deal with higher dimensional problems, it would be interesting to evaluate variants of the planners, for example by randomizing the approach. We have also seen how other clearances can be taken into account in the case where the leg forces have to remain within allowed limits. So it would be interesting to propose other clearances, for example, in terms of the maximum position or orientation error of the platform. Of course, the consideration of collision constraints could be the subject of further research, and equally interesting would be to take into account dynamical aspects in the planner, because there are some manipulators that are designed to work at very high speeds. And this finishes my presentation.